The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, settle down. Let's get started. One announcement. Yesterday we had our first weekly, I would say, minor celebration, and by and large went well. Please make sure that you go to your assigned recitation. If you miss your recitation, you need to get down to see Hillary so that we make sure that we have enough copies of the weekly quizzes on hand. If you've joined the class, you have to check in with her. She's down the hall here in room 8-201, and you will be assigned to a section. What else do I have by way of announcements? Oh, yes, just reminding you, this was from 2003. See, it doesn't change. It's the same S block, P block, and D block elements. Right? So that's coming up a week from tomorrow. 2 celebrations next. And, of course, the contests with hot prizes. All right, let's get down to business. Last day we looked at the Rutherford-Geiger-Marsden experiment. Oh, there's one other one. Oh, yeah. If you look at the readings, there's this one section called the archives. My predecessor, Professor Witt, wrote a set of lecture notes, and they look something like this. And some students have said that they find these a little more expository in certain sections on certain topics than the book to be. And I have no preference, but if you take a look at this, it'll say LN1, Lecture Notes 1. If you go to this, read this. If you find that's helpful, good. If you don't find it helpful, then stick with the book. Just letting you know what that is. All right, so last day we looked at the Rutherford-Geiger-Marsden experiment in which a high-energy beam of alpha particles bombarded a thin gold foil. And on the basis of the scattering results, namely most of the particles went through with minor scattering, and a tiny fraction of them were scattered through large angles. The Thomson plum pudding model was rejected in favor of Rutherford's nuclear model of the atom. And then subsequently, Bohr came up with a quantitative representation of the Rutherford nuclear model, and we were partway through the treatment of Bohr last day when we adjourned. So let's pick up the thread from where we left off. And so just to remind you, the Bohr model is for a 1-electron atom gas phase. So this is either atomic hydrogen, it could be helium plus, lithium 2 plus, Rentgenium 110 plus. It doesn't matter how many protons, there's always only 1 electron. And it's a planetary model. The positive charge concentrated in the nucleus, Z is the proton number. And at a distance r from the nucleus is a circular orbit in which resides 1 electron. It has a charge of -e. And I've just designated them Q1 and Q2. You could have done it the other way, but I had to choose something. So we went through and looked at the constitutive equations here. So first of all, the energy of the system, and this is only going to be the energy of the electron because we assume that the nucleus is far more massive, and so we don't have to get into things like reduced mass or anything like that. So just measure the energy of the electron. Half mv squared is the Newtonian component, and then the Coulombic energy that's stored is Z times E squared over 4 pi epsilon 0 r, where epsilon 0 is the permittivity of vacuum, and it's the factor, the 4 pi epsilon 0 is the factor that allows us to take electrostatic energies and put them on the same plane as mechanical energies. When we run through this, we always end up in joules. Then there's a force balance to make sure that the electron neither falls into the nucleus nor flees and breaks free of the atom. And the force balance is if you put a ball at the end of a string and you whip it around on a tether, you have a centripetal force that's trying to get the ball to break away, and then the string is pulling in. So the pull in this case, is the Coulombic force, and the force that makes the ball want to flee is this mv squared over r, and that must be net 0, otherwise we're going to have a shift in orbit. And then lastly, we have the quantum condition, and this was the the breakthrough of Bohr, where he enunciated that the quantum condition is going to give us this energy level quantization. And this was a big departure from what had been in the past. The only antecedent idea of this nature was the work by Planck, who said that light is quantized. But you know, as I told you last day, who knows what light really is? The Newtonian notion of a ball orbiting was very compelling here, and the notion that the movement of that electron could in some way be discontinuous was quite a major departure. So I left you last day with 3 equations and 3 unknowns. And what I'm not going to do right now is solve the equations, because I've been lecturing long enough to know that that's the way to kill interest, quench a lecture. And so if you really want to go through the algebra, be my guest. You're smart enough to do that. Instead, I'm going to show you the results. But those are the 3 equations that you need. So we have an equation in R, we have an equation in V, and an equation in E. So let's go after them. If you first look at the solution for R, this is the radius of the orbit of the electron. The orbit of the electron. If you go through and solve, you'll end up with this epsilon 0 times the square of the Planck constant divided by pi times m. And it's always the electron. So this is the radius of the electron orbit. This is the mass of the electron times the square of the elementary charge. That whole thing I'm going to group times the square of the quantum number divided by z, the proton number. So what do we see here? Well, everything inside the parentheses is a constant. These are all constant. Pi obviously is a geometric constant, and the rest of these are constants you can look up in your table of constants. And we notice that there is a set of solutions to this. The radius of the electron can occupy various discrete values defined by n. So we say that the radius takes on a plurality of values, a function of n. And furthermore, the functionality goes as the square of n. It's n squared times a constant, where that constant is inside those parentheses. And we notice that because r goes as n squared, it's nonlinear. It's nonlinear. Okay. So this is so important, I'm going to write it down one more time. So the radius of the electron orbit, the radius of the electron orbit takes multiple values. Takes multiple values, and they're discrete. The physicists like to use a different term. When something is discretized, the physicists say it is quantized. So these values are quantized. You cannot continuously vary the radius and nonlinear values. Multiple values. So let's plug in, and because I want to get a sense of scale. So let's look at the simplest one. The most primitive one electron atom would be hydrogen, in which case Z equals 1. So I've just got a proton orbited by an electron. So look at atomic hydrogen. So in that case, Z equals 1. And I'm going to look at n equals 1, which is the lowest number here, right? R scales as n squared. So the lowest value of R is obtained when n equals 1. And this is termed the ground state. The ground state. Okay. So I want to ask, what is the radius of the electron orbit ground state in atomic hydrogen? And if I plug in these values, I'll call this R sub 1. Turns out to be 5.29 times 10 to the minus 11 meters, or 0.529 angstroms. I love the angstrom. It's a great unit. It's a great unit. It's not an SI unit, but I like the angstrom, and I'll show you why. If you try to express this in SI units, well, there's 10 to the minus 11 meters. The SI units go in units, clusters of 1,000. So for example, you've got the meter, you've got the kilometer, you've got the micrometer, you've got 10 to the minus 9 meters, which is the nanometer. And then over here, it's the Goldilocks problem. This one's too big, and then the next one down here is 10 to the minus 12 meters, which is the picometer. So this is either 52.9 picometers or 0.0529 nanometers. And that's no good. I want numbers like 3, 7, simple to remember. So 0.529, this is about a half an angstrom. A half an angstrom. It's good to know. But if you try to publish, you know what happens? In the scientific literature today, the literary lions that control the journals, they'll circle that and say, got to convert to SI units, and so they got to write some goofy nanometer thing or something. I know you think I'm crazy, but I love the angstrom, so there. Anyway, so here it is. Once you know that this is 0.529, this is on your table of constants. It's right on your table of constants, so you don't have to go and calculate all this stuff. Which means if you do your homework with your table of constants, you will know where those numbers lie, as opposed to opening this thing up for the first time on the first celebration of learning on October the 7th, and they're going, oh, there's about 47 entries. They're going, and they're tiny, tiny font. And you're going, where is that thing? Just a word to the wise. So now we know what this is. We know this is 0.529 angstroms. So now I can write an equation for the radius of a one-electron atom anywhere, anytime. R of n, right, is going to be equal to A naught, which is this value here, and it is termed the Bohr radius. The Bohr radius. So you can write it as a function of the Bohr radius times the square of n divided by z. So that's for all one-electron atoms, gas phase. And you can see that as z goes up, the R goes down, which makes sense. So suppose instead of hydrogen, we talk helium plus. What's the only difference? Helium plus has 2 protons in the nucleus, which means that the Coulombic force of attraction between the same one electron and now a doubly charged nucleus is going to be stronger. So that the first orbit's going to get pulled in and all the other orbits are going to get pulled in. How much? By how much are they going to get pulled in? By that much. So this is the functional representation of all of that physics. All right, there's 3 equations, 3 unknowns. Now let's look at energy. So if you go through and solve for energy, you get this one, minus this big monstrosity, mass of the electron, 4th power of the elementary charge, times 8, times the square of the permittivity of vacuum, times the square of the Planck constant, all times the square of the proton number divided by the square of the quantum number. And just to make sure everybody's with me here, I always want to write n here. N equals 1, 2, 3, takes on integer values. And we'll say it again here. N equals 1, 2, 3, etc., etc. So again, we see that E is a function of n. It's discretized. It's quantized. Why? Because once you impose the quantum condition here on angular momentum, it propagates through the entire model. So radius is quantized, energy is quantized, you're going to see velocity is quantized because the quantum condition is pervasive. So E to n, and I'm going to take this whole quantity in parentheses and just call it giant K. Giant K. These are all positive quantities. Mass is positive, and squares and 4th powers of numbers must be positive. So this is K times Z squared over N squared. All right, well, that's good. And we can go and evaluate K. And when we evaluate K in SI units, we get 2.18 times 10 to the minus 18 joules. This is joules per atom. Or you can multiply this by Avogadro's number. If you multiply it by Avogadro's number, then that will give you 1.312 megajoules per mole. Megajoules per mole. So that's the energy of the electron in the ground state of atomic hydrogen. And then we can mediate that with Z and N and go to electrons that are outside the ground state, above the ground state, or ground state electrons in atoms that have more than one proton or both. And so let's take a look at the graphical representation of that. So instead of Cartesian coordinates, because this is This is spatial distribution. I'm going to go to energy coordinates, give you an energy level diagram. So again, not to scale, not to scale. Because this thing goes as 1 over the square, so that's going to be messy. So let's start here. And on the left side, I'm going to designate the energy. And on the right side, I'm going to designate the quantum number. I'm going to start down here. That's the lowest energy. You see, these are all negative values, first of all. They're all negative values, because z is a square, n is a square, and k is a positive quantity. So n equals 1 is the lowest state. It's the ground state, and it has a value of minus k. All right? So I'm going to do this one just for atomic hydrogen. Okay, so I'm going to write atomic H. So now z equals 1. All right? You can do it later for z equals 2, 3, whatever. All right, so this is atomic hydrogen. So ground state energy is minus k. What happens if we go to n equals 2? N equals 2, it becomes k divided by 2 squared, 4. So it should be 3/4 of the way up. I'm not going to go quite 3/4 of the way because I want to leave room for some fine structure. That's why it's not to scale. All right, so this is minus k over 4. What if we go to n equals 3? Well, it's not symmetric here. It's nonlinear, but this should be really what? Minus k over 3 squared is 9. And you get the picture. 3, you can go 4, 5, and so on until n equals infinity. What happens at n equals infinity? I've got minus k over infinity, which is vanishingly small, 0. And where is the electron when n equals infinity? R is n squared times the Bohr radius. That's a great, great distance away. What does it mean? Physically, it means that the electron is so far away that it's no longer bound. It's no longer part of the atom. And when it's no longer part of the atom, and the potential energy that's stored is as a result of the charges coming together from infinity. I'm starting to talk like someone out of 802. You know, what's the energy if I take 2 charged particles at infinite separation, I bring them into some finite separation? Voila, there it is. So when they're at infinite separation, there's no energy stored. Hence, you are at that point. So n equals infinity means R equals infinity, which means E equals 0. There's no stored energy, so this means the electron is no longer bound. The electron is no longer bound, and therefore, if it's no longer bound, we have a term for it. It's called free. It's a free electron. Free electron. And if the electron is free, then the atom is electron deficient. Free electron. So if the electron is free, that means the atom is now an ion because it's lost an electron. It's no longer net neutral. Or we say the electron, or the atom has turned into an ion, or the electron has been ionized. Ionized. Okay. And what's the energy for that? We can calculate what that energy is. It would be called the ionization energy. So if I started with an electron down in here, and I sent it all the way to infinity, see, that's in energy space, which is equivalent in Cartesian space to go from here to infinity. Same idea, right? But you see the models? This is Cartesian. You know, we're thinking about, it's like a map. This is energy coordinates. It's different. And you're going to be able to think from one model to another. What's the energy consequences? What are the Cartesian consequences? Until we get to the point where there is no Cartesian representation because the abstraction level is too high and we'll have to content ourselves with this. So get comfortable moving from there to there, and then someday we're going to say, it's too complicated, there's no Cartesian thing. We'll be comfortable by then with this. Okay, so now we're taking an electron from here up to here. Well, we ask, what is the ionization energy? The ionization energy must equal the delta E of the transition. The delta E of the transition. So what's that? The delta E of the transition is going to equal always E final minus E initial. E final minus E initial, which is equal to E at infinity minus E1, the ground state. Well, E infinity, we just said, is 0. And the ground state energy is equal to minus k, so minus k is k. So you also get the energy from infinity down to ground state is the ionization energy. So we can define the ionization energy define ionization energy in terms of this transition. Define ionization energy as the minimum energy to remove an electron. To remove an electron from the ground state, of an atom in the gas phase, atom. So that means there's no solids, no liquids. There's no work function here. There's no lattice energy, and so on. So there's a definition of the ionization energy. And we can be a little bit more elaborate, even though right now I'm just going to do a little break here, so I don't want to mislead people, but just an aside, because I'm nonlinear. I can have multiple conversations at once, and you are capable of stacking. So we're going to break now. We're not going to talk about one electron atom. We're going to follow the thread of ionization energy. So I'm going to take lithium, which in its normal state has 3 protons, 3 electrons. So I'm going to take lithium gas, and I'm going to ionize it and make lithium plus. So this is a lithium plus ion in the gas phase. It's still got 2 electrons, right? So this isn't Bohr model stuff, but anyway, here we are, plus electron. So the energy for this action would be called the ionization energy, because I took a neutral atom and I pulled an electron out of the ground state and so on. So this is ionization energy. But now I can continue this process, and I can take lithium plus, right? And I can lose an electron from that, which will then give me lithium 2 plus. And this is called also an ionization energy. This is called the second ionization energy. So this is the first ionization energy, but just as when you write an equation, if the coefficient is 1, you don't write the 1. You just put, I don't write 1 lithium here. I know it's 1. This second ionization energy. And then I can keep stripping away electrons, and I can take lithium 2 plus in the gas phase and take away that electron, leaving me with just the lithium nucleus, lithium 3 plus electron. And that's called the third ionization energy. Okay. Now, what can we say? What's the relationship here between any of this, except the definition, and the Bohr model? Well, the Bohr model applies only to 1 electron atoms. Are there any 1 electron atoms on this board? So we can calculate the energy, the third ionization energy. We can get that from the Bohr model. From the Bohr model. You can do it in your head. Do it in your head, right? It's K times Z squared right here. It's going from 1, so if this is 2.18, it's going to be 9 times that, right? Trivially. Okay, so this is just 3 squared times K. And this one you got to get from the literature. So you're going to go to primary sources, which is why you're going to learn how to use the proper database. And this one here also you get from the literature, but this is on your periodic table. Your periodic table, one of the data points it gives is the first ionization energy of all of the elements. And so even though lithium normally is a solid at room temperature, the ionization energy for lithium, as given on your periodic table, is for this reaction. It's for the gas, right? So that's all there. Anyway, so that's a little aside. All right, now the last quantity that we could get from the Bohr model is V. V, the velocity, and I solved for the velocity. We don't talk about this very much, but we're going to just do so once today. And here it is. So I went through the algebra, and you get NH over 2 pi mr, where r is the radius. There's the quantum number. This is quantized as well. So I regrouped this, and I already have a nice, cool expression for r in terms of the Bohr radius. So I use that, because that's on the table. So this is 2 pi times the mass of the electron times the Bohr radius, half an angstrom, see? Half an angstrom, times z, proton number, divided by n, where n equals 1, 2, 3, and so on. So let's, again, get a sense of scale. So let's try for sense of scale. Sense of scale. Let's do velocity of the ground state electron in atomic hydrogen. So that means z equals 1, n equals 1. So I plug in the numbers, and I get V1 for hydrogen, atomic hydrogen, gives me 2.18 times 10 to the 6th meters per second. 2.18 times 10 to the 6 meters per second. I don't know, is that fast? Is that slow? I don't know, but I do know this much. I know that the speed of light is equal to 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. So 10 to the 8th divided by 10 to the 6th, 2 and 3, that's roughly 1, speaking as an engineer, who cares? So this is about 1% of the speed of light. 1% of the speed of light. That's pretty good. That gives me something I can hang on to. So I would say that if this thing's zipping around at 1% of the speed of light, I would say that's relatively fast. Let me tell you that one more time. 1% of the speed of light, that's relatively fast. So what that means is, remember last day I told you that Bohr simply dismissed the concept of the use of classical electrodynamics down to atomic dimensions. Well, here's another example of why a lot of these assumptions aren't going to work so well. We're talking about the ground state electron velocity in this putative planetary model of a one-electron atom, and you're already getting into relativistic effects. So just another example that by the way, why do we use the letter C for speed of light? It comes from the Latin word celeritas, which means swiftness. And we get the modern word acceleration, deceleration from that. Okay. All right, so the Bohr model, we've now rolled it all out. We have the energy portrait, we have the radii, discrete, we have quantization, and we have velocities if we ever want to look at those again. Now, what's the next thing we do in science? We compare the predictions of the Bohr model with data. Are there any data to support this? Because remember, all Rutherford said was, plum pudding doesn't make sense. Instead, I'm going to concentrate the positive mass in the center. And then Bohr came along and said, not only is it going to be a planetary model, I'm going to have circular orbits. So now we've gone a long way from Geiger-Marsden. So is there any data? Is there any data? Well, there were data. In 1853, remember, Bohr published this in 1913. In 1853, there was a spectroscopist by the name, I'm not going to tell you his name, Sweden, in Uppsala, Sweden. And his name was Ångström. And Ångström was doing experiments on hydrogen in gas discharge tubes. Okay? So he measured emission from gas discharge tube. And it was filled with various gases, including hydrogen, including atomic hydrogen. Okay? And in order to take his data, what he used was this device here. Oh, there's the Bohr Radius, just an example. All right, he used the prism spectrograph. So here's a gas discharge tube, and I'm going to show you the physics of that in a second. Basically, you've got a pair of electrodes, you've got gas in the tube, and as this cartoon shows, you apply a potential across the electrodes, and beyond a certain threshold potential, the tube begins to glow. And the glow goes in all directions, and it blinds you when you're in the lab. So what you do is you cover this up a bit, you have a narrow slit, and then you force the light to come through in a thin ribbon, and then expose it to a prism. What the prism does is it takes the light and breaks it into its components, sort of rainbow-like, and magnifies the difference between, as refraction goes, different wavelengths will refract different amounts. And then you shoot this across the room. And over there, you've got the only counter that you've got. Well, there's two counters. One is a scintillation screen and an army of graduate students who sit there in the dark. But they're no good because you can't stick them into the publication. You need to have data that people will rely upon. So instead, you use a photographic plate. And if you put even a tiny, tiny angle of separation across a great enough distance, you start to get enough line splitting that you can see. And then you go backwards and you know the geometry here and you can figure out what the wavelength must have been to go this distance, et cetera, et cetera. And these are all color-coded, not because they had color film in those days, but just to let you know that 656 nanometers, if you were sitting there, if you were the graduate student sitting there, you'd see a red line, a green line, a blue line, and a violet line. Okay. So that's how he made the measurements. Yeah. And he published those measurements. And so they lay. And then the story gets a little thicker. In 1885, there's a Swiss high school math teacher. I mean, I can't make this stuff up. This is a true story. There's a Swiss high school math teacher by the name of J.J. Balmer. We had J.J. Thomson, now we got J.J. Balmer. And J.J. Balmer, he loved to play with numbers. And he was studying this set of lines. And he was trying to come up with a pattern. Can you see a pattern there? 410, 434, 486, 656. Do they go as squares? Are they primes? What's the pattern there? So Balmer puzzled over this for a while and finally came up with an equation to represent those lines. So he studied Ångström's data. He studied Ångström's data and found the pattern. Found the pattern. And here's the pattern that he found. He said that if I take, those are wavelengths. If I take instead wave number, nu bar is called wave number, which is the reciprocal of the wavelength. So if I take the reciprocal of the wavelength, I end up with those four lines conforming to a series that goes like this: 1 over 2 squared minus 1 over n squared, where n equals 3, 4, 5, 6. Okay? And there's a constant here, which we're going to designate r. And the value of r, I'm going to put that on the next board. The value of r as expressed in SI units today would be 1.1 times 10 to the 7 reciprocal meters, right? Wavelength is a meter. Reciprocal wavelength or wave number must be reciprocal meters. So how does all of this support the Bohr model? Well, in order to explain it, I've got to first tell you what the physics of the gas discharge tube are. So let's go inside the gas discharge tube and understand those physics. So here's the gas discharge tube. It's made of borosilicate glass, and we fill it with gas. And in this case, the gas is going to contain, among other things, hydrogen. So this is a hydrogen gas phase atom. And this is probably at low pressure. And then I said I need electrodes. Well, I've got to get the electrodes inside, so I've got to have a really good glass blower who can make a glass-to-metal seal and have a feed-through to an electrode. So this is still a vacuum seal. How do they get the gas in the first place? They don't show you this in the books. I'll tell you, because I did this in my PhD. What you do is you have a little side tube here. You evacuate. This goes to a vacuum pump. And then over here, you have a gas source. You evacuate, put in the gas to whatever pressure you want, and then the glass blower disconnects this, pulls this down to reduce pressure, and seals it. But the books don't show you that. That's a secret. Okay, so. All right, so we've got a gas at low pressure, and I've got an electrode over here and an electrode over here, and they're connected to a variable voltage power supply. So I'm going to put an arrow with a V, meaning it's variable voltage. I can change the voltage. And this convention, this is the negative side, so this means the electrons leave the power supply, go like this, which means this electrode will be negative, and this electrode will be positive. And thanks to Michael Faraday, we will call this one the cathode, and this one we will call the anode. Yeah. Now, what happens? We start turning up the pressure, turning up the voltage rather, low pressure here, but electrical pressure is voltage. The voltage gets high enough, eventually the electrons will boil off the cathode. And this is a gas at low pressure, and they will accelerate from rest and go all the way across the tube and crash into the anode, and we complete the circuit. But if there's a gas in here, some of these electrons are going to hit the gas molecules. And when they hit the gas molecules, if they have enough energy to do so, they will cause electrons inside the gas molecules to be excited. And if they're excited enough, the electrons will jump up to a higher energy level. But they can't be sustained because this is a ballistic collision. It's a one-of. It's like a bowling alley. One ball, one pin, one impact. Now the pin is in the air. What happens to the pin? It falls back down. Why? Because gravity pulls it down. In this case, you've got the energetics pulling the electron back down. Now the electron goes from high energy to low energy, and when that happens, the energy difference is given off in the form of a photon. So I get photon emission when this falls back down. And this photon has a wavelength. What I'm going to show you is that the set of lines that you get from exactly this configuration using this equation give you the Balmer series. So now you've got a model that Bohr postulated for atomic hydrogen, a one-electron atom, that exactly predicts that set of 4 lines, which were measured 50 years before. So let's go. So first of all, let's get the energy here. And I'm going to get the energy of this electron. This electron I'm going to call a ballistic electron. Why do I call it ballistic electron? Because it's not bound. It's free. It boils off the cathode, flies through free space, and crashes into an anode. Clearly, it's not part of an atom. But there's a second electron in this story, and it's the ground state electron in hydrogen. And it lives here. It lives here. So what's the energy of the ballistic electron? Energy of ballistic electron. Well, that's just half mv squared. And where did it get its energy from? It got its energy from the power supply. And what's the electrostatic energy? It's the product of the charge on the species times the voltage through which it was accelerated. So away we go. I know the charge on the electron is minus E, whatever the voltage is here. It's 1 volt, 10 volts, 100 volts, whatever. Away we go. By the way, I'm going to show you just one other thing in terms of order of magnitude. I mean, the kinds of voltages you see along here are 1 volt, 10 volts, that sort of thing. So suppose, to get an order of magnitude, suppose I took one electron, or a charge, let me correct that. Suppose we had a species of charge E. So in other words, it's only 1 times the elementary charge. Species of charge E, and influenced by voltage of 1 volt. So this is 1 in the voltage units and 1 in the elementary charge units. How much energy would that be? That's equivalent to making 1 volt and accelerate an electron from rest across this gap. And the result would be, the energy then would simply equal 1.6 times 10 to the minus 19, 10 to the minus 19 coulombs times 1 volt. And what's the energy going to be? Well, I got coulombs times volts, and I don't know, how do I convert one to the other? I don't have to. Why not? Because that's an SI unit, and that's an SI unit. This is an energy, so with impunity, I write 1.6 times 10 to the minus 19 joules. That's the beauty of SI units, okay? So that's the good news. I know it's joules. The bad news is I hate this number. It's a stupid number, 1.6 times 10 to the minus 19. It's crazy. Why don't I come up with a number like 3, 7, yeah? So what I could do is I could define a unit such that when the elementary charge is accelerated across the unit voltage, I would call that unit 1 electron volt. And so somebody thought of this before me. And hence, this is the unit of the electron volt. It takes these crazy things that we've been spewing here up until now and rationalizes them to numbers that people can carry around in their heads. So what's K now? K is 2.18 times 10 to the minus 18 joules. Yuck. Let's convert that to electron volts. So I divide by 1.6 times 10 to the minus 19, and I get 13.6 electron volts. You'll remember that on your deathbed. Ionization energy of atomic hydrogen. Maybe we don't have to give out tables of constants. You just know this stuff. It's okay. All right. Now, one last thing about this. See, so this has got gas in it. This is the cathode. And this beam of electrons, back in the 1800s, there was a popular term. It was called the ray. So instead of a beam of light, people referred to the ray of light. So then when they got to particle beams, they talked to them as rays. So this is now not an electron beam, it's an electron ray. And it comes off the cathode, and it's in a vacuum tube. So this could be called a cathode ray tube, a CRT. Now, See, I could flatten this, and I could spray it with phosphors, and then I could put some charged plates here. And, the electron's got a negative charge. So if I charge these plates, and I was clever about how I charged them and varied the charge, I could raster the electron beam like this about 30 times a second, all up and down the screen. And then I could put some program signal in there, and I could sit here, and I could watch TV. It all started with the gas discharge tube. It says nothing about the content, unfortunately. Very nice physics, but no content. All right, so now we've got the electron. The electron's moving, the ballistic electron. Now I want to look at what happens when the ballistic electron smashes into one of those hydrogen atoms. So let's go back over here. So here's the incident particle, and it's going to be an electron in this case. So I'm going to designate this electron. Here's my ballistic electron. Okay? So here's the incident electron. And this is ballistic, just to be clear. It's the ballistic incident electron. Now, this is a mixed metaphor here because I'm representing this in Cartesian space, but I've moved into energy space. So some people are going to get really upset because they're going to say, well, how can you see this is Cartesian? This doesn't matter. It's my lecture. It's my model. It works. I'm the professor. So we've got this mixed metaphor here, but anyways, it helps a lot. All right, so what happens when this thing comes in? Depends on how much energy it has. Depends on how much energy it has. Now, if the incident energy, if E incident is tiny, nothing happens. This thing just zooms right on through. But if the incident energy, if E of the incident ballistic electron is greater than delta E for any transition that's feasible, and in this case I'm going to assume I don't have thermal distribution of electrons. If I gave you Avogadro's number of hydrogen atoms because of the thermal distribution of energies, and we'll come back to this later, there might actually be at any moment some electrons that are thermally excited above the ground state. We're going to forget about that for now. We're going to spiral up the learning curve here. So first time we're going to assume all the electrons are in the ground state. If I don't have enough energy to go from n equals 1 to n equals 2, nothing happens. If I have more than enough energy to go from n equals 1 to n equals 2, I will take that energy. And the electron will jump, steal that amount of energy, and then this thing moves on, and I'm purposely making this vector shorter than the incident vector with that amount of energy robbed. And this is called the scattered electron. Go back to the bowling ball analogy. The bowling ball comes in with a certain energy, hits the pin, continues to roll, but you know that there's a loss of kinetic energy in the bowling ball. That's what we're seeing here. It's purely ballistic. Okay? Now, let's say we do have more than enough energy. Suppose I had enough energy to go from n equals 1 halfway between n equals 2 and n equals 3. There's only n equals 1, n equals 2. I can't take the electron up to n equals 2.3. It's unallowed. These are the only allowed states. So that differential amount of energy then resides with the electron that's ballistic, and it moves on here. So we've got conservation of energy here. We can say that E incident will then equal the energy that's lost in the transition plus the energy that's still left with the scattered electron. All right? And we can calculate what that transitional energy is. That transitional energy is going to equal half mv squared incident. This is the velocity of the incident electron. Will then equal, what's the energy to go from n equals 1 to n equals n? Whatever it is, it's minus k times z squared. If it's hydrogen, z is 1. It's going to be 1 over nf, the final quantum number squared, minus 1 over the square of the initial quantum number. And then what's left over after this has been robbed from the incident ballistic energy is a half mv squared of the scattered ballistic electron. Right? And the quantization dictates that only if E incident is greater than delta E going 1 up to n. Here I'm assuming everything's in its ground state. Later on we're going to be more sophisticated, but for first time through, if all the ground state electrons, I have to have enough energy to go at least to n equals 2. I can go to n equals 3, n equals 4. In principle, I could have, if this thing had more than 13.6 electron volts, what would happen? It would kick this electron out, gone. And you'd have 2 free electrons. All right. So if it's greater than this, then we will get, the consequence is electron promotion. Promotion. Okay? So we're moving along, but this excited state is unstable. This excited state is unstable because it's like the bowling pin that got thrown up. So what happens? The electron's standing up there at n equals 2, for example, looking down to n equals 1, and it falls. And when it falls, it gives off radiation, and that radiation is conservation of energy there. And what we know is when it gives off the energy of the emitted photon, the energy of the emitted photon must equal delta E of the transition falling from 2 to 1. And we know how to calculate that. That's just that thing flipped around. And this thing is equal to what? This is equal to h nu, according to Planck, is hc over lambda, is equal to hc nu bar. And you know what this one is? This is minus kz squared, 1 over, in this case, it's going to be 1 over nf squared, 1 over 1 squared, minus 1 over, in this case, 1 over 2 squared, da da da. And you can generalize this 1 over nf. So where am I going with this? Well, I'm going to flip all of this around, and when I flip it all around, what I'm going to end up with is this equation here. And better than that, I'm going to end up with this equation, and I'm going to end up with this as the constant. And when I get that, you're going to say, Bohr's done it. The data support the theory. So that's what we're going to do. But I think we're going to stop at this point today. So let me just jump. Here, I mentioned to you that if you go, here's on your periodic table, there's the 13.6 electron volts. In case of lithium, this is 5.4 electron volts. 5.4 electron volts. So you can see all the various values. This, by the way, people, no noise. No noise. It's 11:52. I'm holding court till 11:55. I'm simply changing topics. It's not, oh, this is the part where I can talk to my neighbor. What are the rules? No talking, no food, no horseplay until 11:55. Then still no horseplay, gentle talking, no food, no drink. This is a sacred space. I'm not kidding you. You know why? In this secular America, this is sacred space because this is where people learn. The lecture hall is sacred space. Now, here's the 13.6 electron volts, and there's the 1.6 times 10 to the minus 19 joules, and if you multiply those two, you'll get the 2.18 over here. All right. Here's a cartoon showing the photon, higher energy orbit, lower energy orbit, electron emission transition, right out of your book. And there's the postulate 6, and we're going to finish this up at the beginning of the Friday lecture. So here's the whole series, n equals 2 to, n equals, from n equals 3 to 2, n equals 4 to 2, and so on. The various, I'm going to see how that works. Okay. All right, so now I wanted to say that one of the things that we've learned here is that it doesn't matter what the incident energy is here, the emission is characteristic of the energy levels inside the gas. I could, instead of using an incident electron, I could use an incident proton. I could use an incident alpha particle. I could use an incident neutron. Anything that has enough energy to kick this up from n equals 1 to n equals 2 will result in photon emission of this frequency. That means the set of those lines is unique to the target. And this is the beginning of chemical analysis. I can use this to characterize species. To wit, stars. How do we analyze the composition of stars? Well, do we send a NASA spaceship out 25 light years and grab some gas and bring it back to the lab? No. All we've got is the spectrograph. The star is hot. That means thermal excitation. Thermal excitation and cascading down with photon emission, and the lines The lines we get are related to the energy levels within the stars. So from a distance of 100 light years, I can tell you what the composition is. And if there's two gases there, what if there's hydrogen and helium? The helium lines will be there, and they'll be superimposed on the hydrogen lines. Unless they lie directly on top of one another, I'm going to be able to figure out what's there. That's how it works. Now, here's a story of an astronomer, Cecilia Payne, who was the first woman graduate student in astronomy at Harvard, went on to chair the Faculty of Arts and Sciences, awarded tenure, but denied a professorship for 18 years because she was a woman. And in her thesis, she was the first person to figure out that the sun is dominantly hydrogen, not iron, which is what most astronomers thought. Why? Well, because the Earth is made of iron. Meteorites are made of iron. The whole universe must be made of iron. Never mind the fact that the sun's glowing. But, so here's how spectroscopy works. Look at this. See, what does this mean? This is an analogy. What could that mean? Well, they said iron again. I know this is misspelled, but maybe it's just a glitch in the instrumentation. So most people would look at that and say, the message is iron. But it's not about the word, it's about the pattern. It's about the pattern, see? And that's what spectroscopy is. By the way, spectroscopy, you see, if you somehow didn't catch this lecture and you walked in and all you saw was those 4 lines, you know those 4 lines, that set of lines is characteristic of atomic hydrogen and nothing else. By the way, those lines are very faint. This is not to scale. And they're so faint, they're ghost-like. And what is the Latin word for ghost? Spectre. So what is a spectrum? It is a set of ghost-like lines. To this day, the term spectroscopy refers to the ability to study data that are so faint, they're ghost-like. All right, we'll see you on Friday.